Okay, so in today's lecture, we're going to talk about the next clustering model. It's called Gaussian. It's called Gaussian mixture models. So before we actually talk about Gaussian mixture models, let's review something on the Gaussian distributions. So, I mean, I understand you probably have learned this before, but I mean, if you haven't, so this will be a good review for this. All right, so first thing first, the Gaussian distributions. In particularly, distributions. In particularly, we are interested in multivariate. Gaussian distributions. So this is usually being parameterized by, again, the mean and the covariance matrix. So I mean, the sigma here is the covariance matrix. So this mu is in R small d, and this covariance matrix is D by D matrix. In particularly, this sigma, the covariance matrix, is a positive definite matrix. So the PDF probability density function for x given the mu and the sigma is, you need to remember that, 1 over square root of 2 pi power of d, determinant of sigma, exponential of minus 1 over 2, x minus mu, transpose sigma inverse of x minus mu. Okay, so, and of course, if d equal to 1, it goes back to the univariate and the Gaussian distributions. Then the covariance becomes the variances. Okay, so, and obviously in reality, we will encounter many high dimensional Gaussian distributions. So that's why this is very important. In a very special cases, if sigma covariance is actually a constant times the identity matrix. So this is identity matrix when d equal to 2. So the contour of the PDF will be and look like a constant and will be look like a circle. So the contour of this PDF, x1 and x2, will be a circle. So basically, you can think about and so the contour is basically and the contour of the density is basically is the curve that this value, this PDF equal to a constant C here. So, this actually will give you, and on this point, it will have equal probability to generate this endpoint. For this curve, if we have the sigma, which is constant times identity, the contours will be circles. And this is like, and basically this will be a round shape. If you want to generate the data, so in this case is with this specific, and with this specific and covariance matrix, this data will be round shaped. So this is very important because I mean this, and because my contour, I mean, is a circle, and my contour means has equal probability to generate a point. So that means if we actually want to if we actually generate the data, follow this specific Gaussian distributions with this and covariance matrix, the data will be round shape as well. But in general, for the general and sigma, for the general sigma, that's general sigma, this contour will be an ellipse. So basically, this data has a bias and in this directions, basically. So you can see it right here. So this is the cases where the diagonal of sigma is equal to a constant times identity. So this is more like general version of the covariance matrix. So we can interpret things a little bit. I mean, this is, and for example, it's more general version of the covariance matrix. So this contour has different meanings. So you can think about, and this is always an ellipse, and the square root of lambda 1 or lambda 2 of the covariance. So basically, we know this is a positive definite. What you can do is you can just to do singular value decomposition or eigenvalue decompositions. I mean, it will be same. So and that will be u and u lambda u transpose. U lambda U lambda U transpose. U will be orthogonal matrix. So what is the definition of orthogonal matrix? Is U times U transpose is identity here. And the lambda is eigenvalues. So and then that will be a diagonal matrix and with eigenvalues on the diagonals. If we take the square root of the eigenvalue and the lambda 1 of lambda 2 and specify the axis ratio of this ellipsoid, of the ellipse. And also this eigenvector u1 and u2 and specify the rotation of axis. So basically this tells you how you rotate this an axis from x1, x2 to the u1, u2s. So this is actually tells you how you change your coordinate. And also the closer x to the mu, which is the center, the mean. Oh yeah, by the way, this an ellipsoid is always centered at the mean right here, and the mean is the mu here. So the closer x to the mu, the higher and the chance or likelihood to generate x. So basically, right here it's more likely to generate, and this area is more closer to the mu. So and the probability to generate, I mean, point right here is higher compared to the probability to generate in this region. So the key here is if you actually sample this data and that follows, so this, distributions, the generated cluster will be an ellipse-like. So this is basically the data that you will be expected to get. It will be looking like an ellipse. So if you are working with much higher dimensions, it will becomes like something called ellipsoid. So which is high dimensional generalizations of the ellipse. All right. So the issue is how can we learn the Gaussian distributions? So I think you probably have learned something about this in the statistics courses. But let's just quickly review this. So learning a Gaussian distributions. So for example, if you have a bunch of data here, So, and given your training data of x of I from 1 to the n. So these data are in R small d, are drawn from some unknown Gaussian distributions. Say we don't know the mu and the sigma here. and this is also drawn in IID manners. In general, and particularly for this courses, we are not considered a situation other than IID. There will be other and separate courses, and for example, stochastic process courses we will consider and everything generated in a Markovian way. So the goal is how to estimate, approximate mu and sigma. All right, so this is basically we have a bunch of data that like we assume it's like generated from some unknown Gaussians. How can we estimate mu and sigma? So, and you probably have like remembered this. So we're going to using MLE, maximum likelihood estimator. So what we do is we actually generate and then we calculate the likelihood to generate x of I. So the likelihood of mu and sigma generate this x of I is nothing but probability of x of I given the mu and the sigma. So in this case, you need to treat this mu and sigma to be a variable. So this is 1 over square and the square root of 2 pi power of d. Here I'm using the short notation that using absolute value of the sigma. If you put absolute value of a matrix, it's naturally talking about determinant of the matrices. Of exponential of 1 minus 1 over 2 x of I minus mu transpose sigma inverse. Like this. Okay, so and this is the likelihood to generate 1 point. And of course we have to calculate the likelihood to generate the whole sample point. So that means we actually need to multiply all these situations together. So this becomes, we need to multiply this I from 1 to the n of probability of x of I conditional on mu and sigma. Okay, so this actually measures how likely this sample data set is generated from this Gaussian distributions. Right, so we have talked about this. Of course, we don't directly work on the likelihood, and we usually work on and we turn everything from maximize and argue max of mu and sigma of the likelihood. It is equivalent of argue minimum of mu and sigma of negative log likelihood. It is much easier to handle this log likelihood rather than the likelihood itself. So if we actually calculate this log likelihood, So this is equal to minus summation I from 1 to the n of probability of x of I given mu and sigma. All right, so, and we have this, sorry, the logarithm. I missed the logarithm here. Logarithm of probability x of I given mu and sigma. So what you do is you plug in this expression right here. I basically take the logarithm. It will be summation I from 1 to the n. I mean, if you take the, I mean, this is basically 2 pi power of minus d over 2. So d over 2, log of 2 pi minus 1 over 2 summation I from 1 to the n, 1 over 2 log of sigma inverse determinant, take the logarithm, plus you have a 1 over 2 summation I from 1 to the n, x of I minus mu transpose sigma inverse and x of I minus mu. Okay. Right here, this has nothing to do with I, this has nothing to do of I. So basically it just add this same value n times. So that means this is actually n times d. Same here. So this is becomes n divided by 2. All right. So now the questions I actually need to, so I'm going to call this negative log likelihood function. Of course, this would be a function of mu and sigma. So I mean, it's always the cases that we want to take partial derivative with respect to mu. I want this equal to 0. I want partial derivative of NLL of partial sigma equal to 0 as well. But this is not easy, right? So this is hard. So we need to do some modification to make it simpler. So, and let's set things aside and using some other factor to simplify things. The first thing we're going to use is the following result. If we are taking logarithm of determinant of A is some matrix. If we take partial derivative with respect to A, this is equal to A and the transpose and inverse. Okay, so this is the first factor that we needed. The second factor that we needed is partial A of, if we do working on a trace of AB, E is equal to partial A of trace of BA equal to B transpose. The second part is trace is invariant under cyclic permutation of the matrix product. So what does that mean? If we have a matrix A, B, C, the matrix product of A times B times C, so this is in this directions. It's counterclockwise. If we calculate the trace of A times B times C, it is equal to trace of C times A times B equal to the trace of B times C times A. But it is not necessarily same as trace of A times C times B. Because A times C times B, A times C times B is not counterclockwise, it's clockwise. So if we have A times C times B, this is no longer cyclic permutations of matrix product. So this only works if it is cyclic permutations. Number 4. And this A, B, C is not necessary to be matrix. It could be a vector as well. We can treat like column vector row and the row vector being degenerate version of the matrices. So and for example, like we are interested in X transpose A times of X. We know this is scalar. So this is actually equal to the trace of X transpose A times of X as well, because this is, degenerate version of 1 by 1. This is actually equal to, we can take the cyclic trend and permutations. This is equal to trace of X transpose. Wait. X and X transpose of A. Right? Because we think about X as being a column, right? So this is a row, this is matrix, this is a column, right? So, and this becomes a column, it becomes a row, then becomes a matrix. So the difference is X transpose A times X is a scalar, but X times X transpose times A is actually a matrix. But if we take the transpose, that will be the same. Number 5, determinant of A is equal to inverse of, so 1 over inverse, is 1 over determinant of inverse of A. Okay, so this is, we can take advantage of this identity here. All right, so with that, we are going to be using all these information here. Here, and you can see this is the structure of X transpose of A of X right here. So we are going to take advantage of this. Okay, I think I made a mistake here. Log of 2 pi here, log of 2 pi. Wait, did I forgot something? This is sigma. Wait. That is logarithm. Just a minute. Yes, that's correct. My notes is missing the minus here, so it should be a minus sign right here. But that doesn't matter because this whole thing is a constant. All right, so let's rewrite things a little bit. So this whole thing right here, right, is equal. So like negative log likelihood can be written as minus nd over 2 of log of 2 pi minus n over 2 log of determinant of sigma inverse plus 1 over 2. Here we're going to using the trick that we'll talk about. Summation I from 1 to the n, trace of x of I minus mu, x of I minus mu transpose, and a sigma inverse. Okay, so you can think about A is your sigma inverse, and the other one is just your x. So here is a mu and a sigma right here. So here I'm going to use another trick is I'm not treating the sigma. I'm treating the variable as a sigma inverse here. So this is something that will help you to do calculations because everything actually shows up is the sigma inverse, not the sigma here. Okay, so the first thing, I mean, because sigma is always positive definite, it's always invertible. So that's fine. So the first thing is partial NLL, partial mu. So you can see only matters is in the trace terms. So you can see right here, so this is, wait a minute. So this is basically, and you can directly take derivative right here. So this is and nothing but a quadratic form, right? So, and I assume you already did something like this before in your optimization courses. So this is summation 1 and 1 to the n. I think I need sigma inverse divided by 2 of x and mu. And I want to remind you, sigma is positive definite. So this and sigma transpose is sigma itself. So it's a symmetric matrix. So its inverse is also a symmetric matrix as well. So it doesn't matter whether you take transpose or not, it's itself. So if we assign this to be 0, because sigma is right here and the sigma inverse is also positive definite, this indicator we can just tells me this has to be, I can move out the sigma inverse out and everything inside has to be 0. And that indicates the MLE of mu hat is nothing but empirical mean. It's 1 over n of summation I from 1 to the n of x of I. So this is, I mean, it's nothing but an empirical mean. Now the second one, if we want to take partial derivative on the mu inverse, the sigma inverse. So this is the constant. So this is minus n over 2. We know log of a, I'm determining of a is a partial, and with respect to partial a here, it's a inverse transpose. So this is your a here, right? So this is n over 2. Inverse of minus t plus, now this becomes the following things right here. So you can treat this is one matrix. This is another matrix here. So basically trace of AB, take partial derivative with respect to A. So this is 1 over 2 summation I from 1 to the n of that matrix here. Right, so this is basically what you got. Right here, this is nothing but sigma, so we are getting minus n over 2 sigma plus 1 over 2 summation I from 1 to the n of transpose. So then the MLE is the sigma hat is equal to 1 over n of summation I from 1 to the n of x of I subtract. I mean, since we don't have the true mean, so we are going to using the sample mean to replace it. So this will be the mu hat and x of I minus mu hat transpose. So this is sample mean. This is nothing but sample variances, sample covariance matrix. Right, so this is already well known already. And we also know this MLE is slightly biased because because the expectation of sigma hat is not equal to sigma. So so the actual and the actual unbiased one is you need to change this 1 over n to 1 over n minus 1. So this is the, I mean, this is the trick that that you probably have seen this many times on the univariate and Gaussian distributions. Very similar argument will follows for multivariate Gaussian distributions as well. All right, so this is basically we're using the MLE actually to find out the MLE estimators for the multivariate and the Gaussian parameters, and which is basically the mean and the covariances. In the next part, we are going to actually implement this from scratch to see how good of our like MLE estimations.